Sounds good. Thank you very much. And thank you all for your interest in hearing about our research today. The plan will be that I'll speak first for about 20 minutes, 25 minutes, just giving you an overview of the work that we do. And then all the questions will be answered by James and Alicio. So a great chance to introduce them to you. James is to my immediate left. James is the postdoc supported by this project. James comes from Australia. And then Alicio Ruiz Guzman. So Alicio is a PhD student originally from Mexico, joining our lab in this project as well. So it's great to be able to present their works to date, and then fire them up with questions over the remaining part of the time. Within Wired, remote sensing has a number of different roles to play. Both of the projects that we have are really under this idea of risk assessment. So how can we assess the risk to the network of extreme weather events, and how can remote sensing technologies be used to help understand those risks? And the way we've approached that topic is through two scales. One's quite a broad scale assessment, which really focuses on land cover change, and in particular fire. So how is fire presenting risks to the network across the entire Pacific Northwest, and how can we understand that risk? And then changing scales completely, the second project within Wired is individual tree scale. And so it's very much around how does an individual tree scale present risk to the network. So two very broad scales, one postdoc and one PhD project looking at that. So remote sensing today, we are blessed by a huge number of Earth observation satellites that go over the Earth every day. Every day, there's about 250 different Earth observation satellites that are collecting information about how the land surface is changing. So really, how these satellites have been going up since the 1970s. So in some cases, we have over 50 years worth of information about how land cover is changing across the planet. One of the key satellites that we use is Landsat. Landsat's an American satellite originally launched by NASA. The first one launched in 1972. The most recent one launched in 2021. We have this continual record from this satellite, and it's designed to give us information at a landscape scale, 30 meters by 30 meters. And this data is free and open, so we can get it anywhere in the world over this archive time. So it's quite a unique satellite series that we can harness to understand how the Earth is changing. And here you can see the build-up of that archive since 1972. So in Canada, we're blessed because we're so close to the United States. Obviously, the data in the US was being collected very quickly, and as a result, Canada got collected very quickly. So we've got an extensive record back in time with over 1,500, 1,700 images since 1972 that we can analyze to see how the land surface has changed. Our focus here through Alicio's project is obviously the Wired area of the Pacific Northwest. So we're looking broadly across all the states and provinces that cover Western North America, and that's our focus area. So we're trying to look to see how are the forests changing across the Pacific Northwest in response to fire, and how might that influence where the risks are associated with the transmission power network. So Alicio's project is going away and extracting all of these data sets from those archives and are looking at that land cover change. Here's an example of just all the data that he's pulling down. So this is terabytes and terabytes and terabytes of imagery that we extract from the archive over the Pacific Northwest to go and look for change. The benefit of having imagery so often, and the fact the imagery is free, allows us to do change detection. And the way we do that is, rather than seeing a before and an after, the way we think about it now is continual change. We've got a pixel, and we're seeing that pixel observed from the 1980s all the way through to today, and we can track that pixel through time. We can track to see if that pixel, or how green that pixel is, and by really understanding what has happened to each of those individual pixels over time. So obviously, if a pixel is unchanged, it's healthy forest, and it's stayed healthy forest over 25 years or 30 years or 40 years, then it's going to be a very stable greenness over time. The benefit here is that we can also find noise very easily, because noise, the greenness might go up, the greenness might go down, but very quickly it will return back to its value. So extracting these archives every single time step and looking at those changes over time allows us to very quickly detect noise. But most importantly, we can detect change. So here's an example of pixels over time. A fire event happened in the 3rd year. We can very easily see the fire event because it massively changes that greenness signal. And then we can track the recovery of that greenness signal over time as the forest is recovering. So Landsat data is very well suited to doing this because it's got a 30-meter pixel. We've got an image every 16 days. So we've got multiple images every year, and then we can track the yearly pattern of these fires and harvesting as they happen. So here's just an example, annual composites of all this Landsat data together, still some noise in places. Some places like 2006, there might have been smoke through most of the summer. The benefit here, though, is because we have these long time series, we can then interpolate between years to give us these very high quality mosaics. And from that, we can very easily see when was there a fire and when is it recovering, and we can track that over time. This will be a graph then. Here's different types of forest, depending where they are in the Pacific Northwest. We have some sort of greenness index or some sort of spectral index over time. Before the fire, it's going to be very green. There's going to be some sort of fire event. The depth of the change in that greenness is going to be indicative of how severe the fire is. And then these stands will recover over time. We can track that recovery if we wish. But for this project, it's really around detecting the fire and mapping those fires over time. Eliseo has to deal with terabytes and terabytes and terabytes of data. So his project is working within Google Earth Engine. Google Earth Engine sort of sits behind Google Earth. Many of us are used to Google Earth and looking around, looking at imagery. Behind that is a very large open processing data system called Google Earth Engine. And it has all the Landsat data in it. So Eliseo is actually using a new algorithm, which is called 3i3D, and it uses 3 indices to go away and look for change. So on those graphs I showed you so far, there was just greenness and then a change in greenness. And there's been a number of papers published on how that can be used. Eliseo is using a new algorithm that tracks 3 different indices, not just greenness, but he also tracks moisture, stress, and also detects indices that are sensitive to fire. And if all 3 of those agree that there's been this drop, then that's a much more solid indicator of fire. Of course, because across the Pacific Northwest, we have other disturbances as well, like harvest, like wind throw, other things that are happening to the landscape. So the benefit of Eliseo's approach here by using 3i3D is hopefully we can predict when it was a fire, because that's the particular focus that we're interested for Eliseo's project. So over time, we apply this every year. And here's some very initial results from Eliseo doing this over Pacific Northwest, so hot off the press. We can see here, this is the pixels flagged as having disturbance from 1985 through to, in this case, 2022. 30-meter spatial scale. So across the Pacific Northwest, you see these little patches of color. When we zoom in, we see all that richness. So there, that's a focus there in British Columbia. There we can see all the different pixels detected as changed that we believe are fire, and the color represents the year. So you can start to see how these patterns of fire sort of connect with each other over time as the fires burn in different years across the landscape. And this will continue to be processed and developed over the next few months as Eliseo goes and gets the algorithm more fine-tuned to cover all the vegetation types across the Pacific Northwest. So the algorithm needs to be sensitive to fires in British Columbia, which are going to be very dense forests, perhaps, compared to fire in California, which are going to be drier, more open forests. So a lot of this 3i3D needs to be tuned to the different ecozones across the Pacific Northwest, just to make sure that we're really sensitive to the fire that we're seeing. And then Eliseo will go and verify this using aerial imagery, using Google Earth imagery, using other satellite imagery to make sure that we are detecting fires when we should, and we're getting them right by year. The cool thing that we can do then is we've then mapped every fire. So this project is not about mapping the fire, it's translating this to fire risk. So the way we think about fire risk is we think about fire regimes. Different parts of Pacific Northwest have different fire regimes. And a regime tells us how often we expect a fire, how big that fire is likely to be, and how often that fire should return to the landscape. So some landscapes across the Pacific Northwest burn quite often. Fire is a very important part of the ecosystem. Other parts of the Pacific Northwest, fire shouldn't happen really at all in our lifetime. So we actually can put all the fires, how often they are and how big they are, into a model, a pretty simple model like this exponential curve up here on the left. And from that, we can then come back and say, this is the type of regime that we expect in these different areas across the Pacific Northwest. Some areas we expect fire more often. Some areas we expect fire less. And of course, the cool work is that we can populate these models from fires over the last 50 years. We could also do it over the last 10 years. So we could see how the fire regime is changing under a changing climate. Once we've mapped the fire regimes, we can also go away and look at things like what vegetation is there, what canopy cover is there, what's the topography like. And we can bring together the fire regime with the environment that we're in. And when we bring all of these things together, we ultimately have models of burn probability. How likely is it that a pixel is to burn? So obviously a pixel that's already had a fire is not going to burn again very quickly. It's going to take a while for that fuel to burn back up. Whereas other pixels that have lots of fuel, haven't burnt for 100 years, they've got a certain topography, they've got a certain vegetation type, they're going to be expected to burn more often. So ultimately, by gathering all this remote sensing data, building these maps of fire regimes, Eliseo is ultimately going to be able to go away and say, this is the probability that a pixel might burn. And you can imagine, as we overlay the wired network over these maps, it then gives us a very clear idea of where across the network the forests surrounding the transmission lines are likely to burn. And that then becomes a very useful indicator for management in terms of how we might go and avoid that from burning. And the way we might do that would be to do some harvesting, do some forest management, or even have a low intensity burn that goes away and burns the different areas under a controlled situation that would stop a large fire from coming. So that's the first project that we're doing within Wired, and that's the work that Eliseo is leading, this very broad scale work. I'll spend the rest of the time talking about the much finer scale project, which is James's postdoc. So now we're changing scale. We're not thinking about the Pacific Northwest as a whole. We're now thinking about individual risk to an individual transmission line from an individual tree. And we know that this is very significant. So this is data from BC Hydro, which is British Columbia Hydro, the power management agency in the province of British Columbia. They provided us with their transmission line data and their outage data. So here's a map of all the vegetation in British Columbia. We're very forested. You can obviously see where the transmission lines are because that's where the lines are over the map. And the color is telling us the number of the types of outages that we've had across the network over a 5-year period. You can see the data says that there are 70,000 power outages across the network. 50% of those were caused by vegetation. And you can see 75% of those were caused by a tree falling on the wire. 23% were a branch falling on the wire. And 2% of the cases were encroachment. And that's where the vegetation beneath the wire is growing up to the point where it's touching the wires themselves. So trees are a major problem for causing outages in these types of environments. So there's a constant need to manage the forest on either side of the right-of-way of these power lines to make sure the trees don't cause this problem. So thinking about the vegetation on either side and trying to understand what is the risk is something that we need to go away and do. So currently, BC Hydro and all the different power agencies across the Pacific Northwest would have surveys. They'd either have helicopters or they'd put people and they would walk along these lines to go away and assess the risk. But that takes a lot of time. It takes a lot of effort and it's very expensive to keep doing that. And the other limitation is they just do it once. Is the tree touching the wire now? There isn't really much assessment. Do we think it will touch in the future? And this is the idea of future risk. The way we think about this from a remote sensing perspective is we can map the structure of trees very well. And the way we do that is using a technology called LiDAR. LiDAR is a technology that sends a pulse of light from a sensor, could be a satellite or an aeroplane or a drone. The pulse comes down, it hits the tree and bounces back. And as a result, we get very, very detailed information about the 3D structure of vegetation across the landscape. Now, we don't actually have much LiDAR in space. The vast majority of LiDAR we get is from a plane. So planes fly backwards and forwards over the forest all the time across the Pacific Northwest, building up these data sets of this three-dimensional structure. And it's extraordinarily detailed. So this is an animation that James has done using LiDAR data. So here you can see the extraordinary detail that we're getting. It's a standard forest on either side and a right-of-way down the middle, and he's coloured the power lines red. This has been normalised against the terrain. So we take the terrain and we remove the effect of terrain from the point cloud, which is why it looks flat. And it's also why the power lines look bumpy, because this is the height relative to the ground, not height of the terrain and the ground. But here you can see the extraordinary detail that this technology can provide. Clearly, we can model the trees on either side. We can also model the vegetation beneath. And the exciting thing about James's project is we can try to model what is going to happen here in the future. So James has been focusing on forests in British Columbia. There's a variety of different areas of forest he's been focusing on, simulating edges, the edge of the forest next to a power line. So here you can see different snippets of forest that is taken out, B, C, D, and E. And we've got LiDAR data of these forests. James's approach is working at the individual tree scale. So here's an individual tree from LiDAR data. So there you can see all the points that have reflected back, the laser returns that have come back from every single tree in the forest. And what he's trying to do is model the tree at time 1 and then predict the growth of that tree at time 2. So he's taking the point cloud of the crown, the first time the LiDAR was flowing, and then trying to predict how do we believe that tree will grow and expand as an individual over time. The way he does this is relatively complicated, so I'll let him answer any questions about how it's done. But what he's trying to do is build a shape around the tree and then project that shape in three-dimensional space over time. So he's got multiple LiDAR data sets acquired from a plane. And in this case, as he builds the model, he's got 3 data sets, 2010, 2016, 2022. And because we're lucky, we've got so much LiDAR data set, he can build the model between 2010 and 2016. How much did the tree grow over that time period? And then he can apply the model from 2016 to 2022 and work out how good it was, because we have some real data in 2022 to go and check it. So it's great to have 3 acquisitions to allow him to build the model and then independently verify it using that data at time 3. So here's an example of a tree collected in 2010, 2016, 2022. You can immediately see the types of issues James is dealing with. One is the fact that LiDAR wasn't that good 15 years ago. So the LiDAR point cloud, there's nowhere near as many laser hits in 2010 than there were in the system that used 2016. And in fact, 2022 is even better. So already we've got a problem. with the fact that our data is not necessarily consistent over time because LiDAR technology's got better each year. But regardless, you can still see the tree, and you can still see the fact that the tree is growing. You can see it's got taller, for example, just simply by looking at the point cloud. And we can see more development in the crown over time. So the way James does this is he fits shapes. And these things are called alpha shapes. And they're like wrapping cling wrap over the crown itself. So it's a mathematical representation of the crown through this surface called an alpha shape. And he can tighten or loosen that shape as he wishes, as he fits to each of these point clouds. He has the point cloud that he's going to go away and model. And what he does then is puts the shape around the crown, and then he projects that shape outward into this broader sphere. And what he's trying to do then is work out how each facet of that sphere allows the tree to grow outwards over time. So ultimately, he's predicting how that alpha shape within this broader three-dimensional space can fill over time, training it on the 2010 to 2016 data. So ultimately, every facet on the alpha shape is projected over time to grow. So his model predicts how much is that facet going to expand in X, in Y, and in Z. And he individually predicts how each facet will move. And as a result, he can build the current crown and then project that crown 6 years in advance to 2016, test the model, build the model, and then apply the model to 2016 and test it in 2022. So here's a bit of a sense of how that actually works. He's got his original model there in 2010. He then fits the alpha shape and then predicts that model through to, using the data, builds a model of how that crown is then changed by 2016. Once he has that model, he then applies that to 2016 data to give us how much we think the tree has grown by 2022. So that's 12 years of growth, and then predicts that with the observed data in 2022. And here you can see this is a real crown, so you can see the facets that have been fitted to the crown over time. And those little colored dots are telling us whether we're over or under predicting the growth of the tree at that time period. So you can see there, red, where sort of the canopy is slightly bigger than it should be, and blue, we're slightly predicting it less big than it should be over that 12-year period of time. So James has already published his first approach of doing this, and this was on individual crowns, much like I've shown you here. And that work has been published already in Remote Sensing Letters. And you can see we're very good at predicting what is happening to the height of that tree, what is happening to the volume of that tree over time, and then the area, the two-dimensional area, which is sort of looking down on the crown and seeing how the silhouette of the crown has changed. You can see it's not perfect, so we're not getting asked for height. We're very accurate, but for volume and crown area, we're explaining 50 to 60 to 70% of the variance, and that's for an individual crown. The work James is doing now is recognizing that trees are within stands. So a tree can only fill its space if its neighbors let it. Trees are always surrounded by other trees. So this is bringing in competition. So not only when you predict how the facet is changing, are you predicting the growth, you're also predicting you're also using how far away the tree is from its neighbor. And obviously, if it is far away, it can grow into that space. If it isn't, it can't. And this is very important for wired because the trees we care about are the trees on the edge. So those trees are funny trees because on one side, they've got neighbors in the forest. On the other side, they've got open area, a gap. So these trees actually become quite asymmetric because they can't grow on one side, but they can grow on the other. So by James using this competition factor, where of course the trees on the edge have no competition. They're going to grow much more in that direction than they are inside the forest. And so now he has that capacity to bring in this plot scale competition, which is what he's now working on as part of his work. So this is what James is doing. He's now looking at the competition, which is the second factor he's bringing in. We can also look at things like how old is the forest, because the age of the forest does also dictate how quickly it grows. And then also species. As we start to think about running this across these different forests in Pacific Northwest, then obviously Douglas fir or lodgepole pine or species in British Columbia will be different than species in California. So the species will also have an effect, as well as the local conditions that we're dealing with. So we can bring climate in if we want, and we can also bring, are you on a top of a hill or bottom of a hill? Are you north facing or south facing? Ultimately, this data has been produced by planes. But the other work we're doing for James's project is thinking about drones. So drones are the most logical way to collect this data. Planes go backwards and forwards, but planes are expensive. And we don't have planes flying every year over all of the Pacific Northwest. Really, this is an ideal technology for drones. And the last 3 years has seen a massive increase of drones and LiDAR. So drones can now fly this LiDAR equipment. So here's my research lab proving to me that they can get the drone in the air very quickly. You can see the drone there is a DJI M300. So it's got 4 propellers. The LiDAR system sits beneath that drone itself. We have a GPS that tells us exactly where the drone is. We have a generator to keep powering up our batteries. We have Starlink to make sure we have internet, and off that drone goes. And that drone can fly up and down these power lines, giving us very, very high quality data. So James's approach will then not only be to extract the trees from airborne data, but also extract the trees from drone data. And that will be the logical way we would imagine that our collaborators, like BC Hydro, would then use his models into the future. And ultimately predict these types of images and maps like this. So this is work that's done not by us, but by others in this type of field, demonstrating, yes, you've got trees. The trees aren't necessarily causing a problem today, but this is the future risk. We anticipate that this branch will hit this tree in 2028. So you need to go away and do some sort of treatment to stop that tree from going where it is. So this idea of future risk, the ability of these crowns to grow over time to give us this information. So I hope I've demonstrated to you that remote sensing data has a variety of different ways it can inform upon changes to the landscape, and in particular, changes to forest around the power grid. We have the ability to use satellite data, historical archives, to really give us a sense of risk with things like fire, which is proving to be a major risk of our power lines as we see fires increasing across the Pacific Northwest. And then secondly, we can think about this individual tree at the management scale. What trees need to come down to reduce risk? And it's not only what trees need to come down because of the risk they pose today, it's the risk that these trees will pose in the future. And the ability to use this very fine scale LiDAR laser data to think about the current crown and its growth is really an extraordinary way we can apply this data, and very, very unique in terms of the way these models are being developed and applied. We would love to answer any questions you have. I'm going to immediately let James and Alicio do that as your questions come in. You're welcome to follow us on Blue Sky and email us if you've got any questions, and look forward to any questions that you might have. Thank you very much for your time. Our pleasure. Thank you for the interest in our work and the opportunity to speak, and feel free to reach out to any of us for any future questions you might have.
Yeah, thank you so much. Thank you so much, everyone, and we will see you the next 2 weeks. Thank you.
Thank you.
Thank you.
Thank you.
Thank you so much.